Okay, Math 352, we're back, and we're up to lecture 16. This is the first lecture that we're going to do on a new topic, so we've left our work on linear programming behind for now, and we're going to spend a couple of lectures looking at some more linear algebra, kind of more pure linear algebra. And what we're going to do, and after that, we're going to use what we've learnt in some more applied kind of topics. Okay, so what we're going to look at today and tomorrow and next lecture is the topic of positive definite matrices. Now these are a type of matrix that arise very often in all sorts of physical contexts. So when you're working in applications, odds are you'll come across these matrices and they're very important. So we're going to define them, come up with a few examples of where they come from, and see what we can actually do with a matrix of this sort. Okay, so to start off with, what I'm going to do is I'm going to introduce a couple of examples. They come from some different areas, and the first one is going to be one from electrical engineering, which is circuit analysis. Now, just a disclaimer here, obviously you're not all electrical engineers, and a number of you won't have actually looked at a problem like this before, so I don't expect you to really understand the physical theory here. So if you're in that category, you can just sort of watch along. Won't take long to do the actual example anyway. And otherwise, if you've done this before, if you've done some physics or some electrical engineering, then this might be quite interesting for you. Okay, so what we've got here is a very basic circuit. We've just got a circuit which has resistors in it and a voltage source. So I'm going to give each of these resistors a value, 2 ohms, that's the unit of resistance, 1 ohm, 1 ohm, this is going to be a 5 ohm resistor here, 2 ohms and 1 ohm. And I'll say that my voltage source is 6 volts. Now, when I say I want to analyze this circuit, what I mean is I want to figure out what are the currents flowing through each one of these components. So I'll define two currents around these two loops here. I'll call this one x1, and I'll call this one x2. Now these currents can superimpose so that the current flowing through this 5 ohm resistor, for example, is actually x1 minus x2. So if you apply the standard technique here, which is Kirchhoff's loop law, or Kirchhoff's current law, and any electrical engineers will know this as KCL, then you just basically follow the current around and you drop by a certain amount each time. So first one's going to give us, so if I start here for example, and follow my current around, I'll get minus 1x1, minus another 1x1, minus another 2x1, and then minus 5, and the drop here is going to be x1 minus x2. It gives me 0. Okay, I get back to the same place. So just collecting all these terms together, we get 9x1 minus 5x2 equals 0. Okay, for the second circuit, we choose a point and we follow the current around. I'll start from up here. I get minus 2x2 minus 5, this time will be x2 minus x1, minus 1 x2 equals 6. Okay, sorry, what am I saying? Plus 6 equals 0. As I go through the 6 volt source, I get back to where I started, and I get 0. Once again, rearranging this, we get negative 5 x1 plus 8x2 equals 6. And we can write this as a matrix equation, which we can then solve for x1 and x2. Okay, now I'm going to call this matrix here A. Now one further thing we can do here is, let's say we want to work out the total power, that's the total wattage, consumed by our resistors. Okay, so for those of you who don't know what I'm talking about, we'll be done soon. Well, you know, the formula is the power consumed is equal to the sum over all the resistors of I squared R Okay, so we're going to look at each resistor individually, because it'll combine the 1, and the 2 together because they're equivalent. We get 4x1 squared. Okay, that deals with these three together. Plus 3x2 squared. That deals with these two. Just lumping them together because they're just independently standing in the same circuits. And finally, with that 5 ohm resistor, we get 5x1 minus x2 squared. Okay, which we can do a little bit of jiggery pokery with our algebra, and we'll get 9x1 squared minus 10x1 x2 plus 8x2 squared. And this can be written as a matrix quadratic form, so P equals x1, x2. Following matrix, we've got a 9x1 squared, we've got an 8x2 squared, and we've got minus 10 x1, x2. So I'm going to split that into 2 equal parts. We'll find out why I do that later. Which equals x transpose AX, which is greater than or equal to 0. Okay, sum of squares times positive number has got to be greater than or equal to 0. So we know that for this equation here, no matter what our values of components are, we're going to get that the total consumed power is given by this expression here, which is always greater than or equal to 0. Okay, a second example. Masses and springs. I'm sorry, we're still in physics. That's okay. You've probably had enough of masses and springs from your stage 1 calculus, if you're not in that category, but that's okay. So let's just draw a picture of a spring and mass arrangement. At least these ones are easier to visualize. Got a spring here. It's attached to a mass, which is attached to another spring, which is attached to another mass. Just for fun, we'll have one more, which is attached to another mass, and the last mass is free to float around. Okay, so dealing with the horizontal masses, if you like, they're sitting on an icy, a slippery surface, so that there's no up or down motion, there's just left to right motion and no friction. Okay, so we'll define the spring constants. K1 equals 3 newtons per meter, K2 will be 4, and K3 will be 1. And I'll define the following variables, which are the displacements of the masses from their equilibria. So we'll call that one x1, that one x2, and that one x3. So you can see that when this thing is at rest, x1, x2, and x3 are going to be equal to 0. So what I'm going to look at this time is I'm going to look at the energy stored in each one of these springs. Okay, so if you remember from your first year physics, if you did that, the stored energy in a spring is equal to half its spring constant times its displacement squared. Okay, so let's just be a little bit careful about this, make sure I do it right. So for the first spring, the displacement is just x1. So it's going to be a half times 3x, I'll just put the half outside, 3x1 squared. Second spring, the displacement is actually given by a combination of x2 and x1. So it's going to have to be 4x2 minus x1 squared. And for the third spring, it's going to be 1x3 minus x2 squared. Okay, some algebra follows, and you get a half 7x1 squared minus 8x1 x2 plus 5x2 squared minus 2x2 x3 plus x3 squared. And again, we can write this as a matrix equation. A half x1, x2, x3, and once again it's going to be quadratic form because all of our terms have two x's in them, and then we just fill in the blanks. We've got 7x1 squareds, 5x2 squareds, 1x3 squareds, x1, x2s, that corresponds to these two entries. We've got -8, so we'll split that -8 into two pieces and put them in there. x2, x3s, we've got -2 of those, so once again we'll split that in two as well and put them into those two entries. And there are no x1, x3 terms. So if we call this matrix B, then what we've got is a half x transpose bx, which again is greater than or equal to 0. Okay, we can't have negative energy stored in our springs, so that quantity has to be greater than or equal to 0. Do one more example. Those of you who are in Math 361 have probably seen something like this before. Finite differences for a PDE. So what I'm going to do is I'm going to discretize Laplace's equation, which is uxx equals 0, with a couple of boundary conditions. U of a equals 0. Okay, and what I'm going to do is I'm going to write down my domain. So let's see, I've got x is 0, and I'm going to split it up into 5 points. That will be my, sorry, x, call it x0, not x1. This one will be x4, which equals 10. And in between we'll have some other numbers. So this will be x1, x2, and x3. So basically I'm just taking my straight line, I'm splitting it up into a finite number of points, each of which are separated by a distance h, which here will be given by 2.5. Okay, so x1 will be 2.5, x2 will be 5, x3 will be 7.5, and x4 is 10. At each of these points we want to know what u is. It's probably a temperature, or something like that, or a displacement of something, depending on the context, and u4. So what we want to know is, what are these u0, u1, u2, u3, u4 values? So using finite differences, a little bit of notation, sorry. Notation, u at xk we'll write as uk. Okay, that's why I've said u0, u1, u2, u3, and u4. So uxx at xk is approximately equal to, using central differences, uk minus 1 minus 2 uk plus uk plus 1, all divided by h squared. Okay, and we know from the Laplace's equation that must be equal to 0. So what we basically get here, we just apply this equation at each of our 3 internal points. And we get the following 3 equations. u0 minus 2u1 plus u2 equals 0. Notice I've not written down the h squared because we can just multiply that out onto the right hand side. Second one, u1 minus 2u2 plus u3 equals 0, and u2 minus 2u3 plus u4 equals 0. Okay, I've written something down a little bit wrong here. Sorry, I said this is 10. Maybe I should write this slightly differently. Maybe I should say get my notation correct. It's terrible. U0 equals 10. I just written down my boundary conditions altogether wrong. When x is 0, u of 0 is 10, so that u0 is going to be equal to 10. When x4 is equal to a, silly me, so h will not be 2.5, h will be a over 4, then u is equal to 0. There we go, that's much better. Okay, so we know u0 equals 10 and u4 equals 0. So we have three equations in u1, u2, and u3. What do they look like? Well, you can work it out for yourself, but I'm just putting in 10 into u0 and 0 into u4. I get 2 minus 1, 0, minus 1, 2, negative 1, and 0, negative 1, 2, times u1, u2, and u3 equals 10, 0, and 0. Okay, and I'll call this matrix C. So I've done three examples here, which are seemingly quite unrelated, but each one has introduced a matrix A, B, and C. So your question might be, what do the matrices A, B, and C have in common? Okay, well there are a couple of things. If we look back to the previous page, here's B. One thing you'll notice is that they're both symmetric. Okay, they're both equal to their transpose, and that was actually by choice. I split my negative 10 into two pieces, negative 5 and negative 5, so that my matrix would be symmetric. Likewise with the B, by choice I made that symmetric. And for this one here, this one is symmetric automatically because of our choice of finite differences. So first off, you can see that they're symmetric, which doesn't start with a G. Okay, and what else? Well, we don't have a corresponding expression for the third one, but for the first two, we had x transpose bx is greater than or equal to 0, and we had x transpose ax is also greater than or equal to 0. Right, so it happens that it's also true for this third one as well, although we don't have such an obvious way of just writing it down. Okay, so these matrices are what we call positive definite. Okay, and this expression here is kind of a way of saying that the matrix is positive under a certain context. It's sort of analogous to positive real numbers. If you wanted an equivalent thing for a matrix, then a positive definite matrix is your kind of equivalent. So let's go into the definition here and define it a bit more formally and see what we can figure out about these things. Okay, so we've got a wee bit of intuition for them. We know they're going to be symmetric. A couple of other things we'll note. The diagonals appear to be positive all the time, and they sort of look like they're bigger than the off-diagonal entries as well, don't they? The diagonal entries seem to dominate the off-diagonal entries, likewise here. So we've got a bit of an intuitive picture of what these things are like, but we better actually do some actual maths on it. So let's start with the definition. So I'm going to work back into complex matrix land now. So matrix A, oops, let's try that again, is positive definite if and only if z star az is greater than 0 for all z in Cm, with z not equal to 0. Okay, so I should also say that the matrix A, just make a wee bit more space. and C m by m. Positive definite if and only if that statement there is true. Okay, first off, what does this imply? Well, first, this implies that A is Hermitian. Okay, it should be capital H, sorry. Okay, that just means that it's the complex version of symmetric, remember? A star equals A. Or symmetric, if A is real. Okay, so you might want to think about why that's the case. And let's say we can also change our definition. If we allow that Z star AZ is greater than or equal to 0 instead of just greater than 0, then we say A is positive semi-definite. Okay, so it's not quite as strong a definition, if and only if Z star AZ is greater than or equal to 0. Okay, so if we can relax the definition of positive definite to include matrices for which there is a Z that Z star AZ equals 0, and such a matrix is called positive semi-definite. Okay, so positive semi-definite includes all the positive definite ones, but also allows for some more. A couple of other related definitions. A is negative definite if negative A is positive definite. Okay, I'll often just write positive definite as PD. And likewise, A is negative semi-definite if negative A is positive semi-definite. Finally, if a matrix is none of these things, then we say that it is indefinite. Okay, so the positive, or the definite matrices, the positive, negative, semi, blah blah blah, definite matrices, are a small class of matrix when you look at the field of matrices altogether. So, with your field is a bad choice of words, sorry. Look at all the matrices that you can create. So, there are special cases of matrices that have special properties. Just bear in mind that most matrices you could come up with will be indefinite. Okay? So let's just do a few examples. Okay, so number 1. I, the identity, is clearly positive definite. Why is that? Well, x star ix is equal to the sum of xi squared, which is clearly greater than 0. Okay, so if x is not equal to 0, then the sum of its absolute value entries squared is greater than 0, so the identity matrix is definitely positive definite. Number 2, D is diagonal with dii is greater than 0. Okay, if it's greater than 0, it's obviously real. Well, let's have a look at that. ZH, what am I saying? Z star is dz. What is that equal to? Well, I'll do this one out in a little bit more detail. Z1 bar, Z2 bar, Zm bar, D Z1 bar, Zm bar, no bars. Equals the sum over all of the ones. It's going to be almost exactly the same as the identity case. It's going to be absolute value of zi squared, which once again is greater than 0. Okay, so number 3, D with, so once again D diagonal with this time dii greater than or equal to 0, then D is, sorry, I should have said before D is positive definite. Then in this case D is positive semi-definite. Okay, e.g. 1, 0, 0, 0 is PSD, positive semi-definite, as Z equals gives Z star dz equals 0. Okay, just to round this off, we'll do an example of an indefinite matrix. So if I just write down a matrix with numbers in it, I may as well make it symmetric though, because we're always going to be looking at Hermitian or symmetric matrices, is indefinite, as for example 1, 0, A, 1, 0 equals 2, and we could choose a different Z, 1, negative 1, A, 1, negative 1 equals negative 4. Okay, so for if A were positive definite, then no matter what vector we chose here, so long as it wasn't the 0 vector, we'd get a positive number out. Here we can get a positive 1 and a negative 1, so our matrix must be indefinite. Okay, so we'll look at how to tell whether a matrix is positive definite a little bit later. But for now, let's look at another way we can use this information that we've suddenly got. Okay, so positive definiteness in function minimization. So this example's got quite an optimization flavor to it. Okay, because actually one of the main applications of positive definite matrices is in optimization, so that makes sense. So we'll let f be a function mapping Rm onto R, and f is smooth. Okay, if f is smooth, then it has a Taylor series, and its Taylor series is given by f of x plus some small displacement h is equal to f of x plus h transpose grad f of x plus 1/2 h transpose times the Hessian. Okay, we'll talk about this matrix in a moment because you may not have come across it before. Times h plus some higher order term in h cubed. So this is where the gradient and the Hessian are evaluated at x, and this beastie is the Hessian. matrix. Okay, and let's just write down the definition for that. So in case you haven't seen this before, the Hessian is equal to a matrix G of X, where Gij of X equals the second order partial derivative of f with respect to xi and xj. So it's just the matrix of all the second order partial derivatives of your function. Now, so we've basically got a Taylor series for our function. We've got constant, linear, quadratic terms, and we're ignoring the higher order ones. Now let's say that we've gone through and we've found a stationary point. So let x star be a stationary point of f of x, i.e. the gradient of f at x star equals 0. Now, just to not be confusing here, this is not the conjugate transpose star. This is star like in linear programming, where it means some kind of optimal. Okay, so let x star be a stationary point. That means a point with a gradient 0. Then the Taylor series becomes f of x star plus h equals f of x star plus, well, the gradient term is going to go away because it's equal to 0, plus 1/2 h transpose times the Hessian evaluated at x star, h, once again, plus higher order terms. Now, if our Hessian here, is an m by m matrix, is positive definite, then basically, no matter which direction we go away from x star, this is going to be a small positive number. Okay? No matter what h we choose, this will be a small positive number, so we're going to be going upwards. I stuck my 2 in the wrong place there. Then f of x star plus h is greater than or equal, or greater than, sorry, f of x star for all h with h is not equal to 0 and norm h sufficiently small. Okay, what does that mean? Well, it means that our x star is a local minimum. So grad f of x star equals 0, and the Hessian of x star is positive definite, which is how I'll write that. This implies that x star is a local minimizer of f. Okay. So just note here, a little note on this notation. When I say a matrix is greater than 0, I mean the matrix is positive definite. I don't mean all the elements are greater than 0. What that notation means is that the matrix is positive definite. Okay, so just bear that in mind. Whenever I say that a matrix is greater than 0, I mean the matrix is positive definite. If I wanted to say that it was element-wise greater than equal to 0, or greater than 0, I'd specify aij is greater than 0, or something like that. Okay, similarly, grad f of x star equals 0, and Hessian is negative definite, this means we have a local maximum. And finally, indefinite means we have a saddle. Okay, so what we're doing here is we're doing the second derivative test that you've learnt before in first year calculus, except we're doing it in a slightly more general context here. So that's essentially what the second derivative test boils down to, is a test as to whether the Hessian is positive definite or not. Okay, so it's all very well to talk about positive definite matrices, but if we can't figure out whether a given matrix is positive definite or not, then that's not hugely helpful to us. So I'm going to write down a few tests that we can do that will tell us whether a matrix is positive definite or not. And I'm going to prove these in the problem class on Tuesday next week. So that will be the one on Tuesday the 17th of May. So I'll just state all these results without proof, and we'll look at them in a bit more detail in class on Tuesday. So tests for positive definiteness. Okay, so number one. Well, the number one is basically the definition. For some matrices, like a diagonal one, you can actually verify directly. What am I doing? You can verify directly that your matrix is positive definite by using the definition. Okay, and we did that for our simple examples earlier with the diagonal matrices. However, most of the time that's pretty hard to do directly, so there are some related ones you can do as well. Okay, so another equivalent condition. All eigenvalues of A are real and positive. By the way, all of these conditions are equivalent. Okay, we can do any one of these, and that will tell us yes or no as to whether our matrix is positive definite or not. All principal submatrices AK of A have positive determinant. Okay, so what does that one look like? Well, if our matrix is m by m, then AK is this submatrix here, which is K by K. So if we go through and we work out all of these submatrices and compute the determinant, then that tells you that your matrix is positive definite. Okay, another one. All pivots are positive in naive Gaussian elimination. Okay, so just what that means, naive Gaussian elimination, that just means no row swaps or scalar multipliers. Okay, so it's the kind of most basic Gaussian elimination you could think of. Okay, and the pivots, let's drag that down a little bit. Are the diagonal entries of its row echelon form. Okay, so that's a reasonable test. We go through and we attempt Gaussian elimination on a matrix, and so long as the pivots are diagonal, then so long as the pivots are all positive, then we can tell our matrix is positive definite. Okay, and related to that one is what we're going to look at next lecture, Number 5. Compute a Cholesky factorization. Okay, so this is a factorization of a matrix that's specific to positive definite ones, and basically it's like doing Gaussian elimination, but it takes about half the work. And if our factorization, if it succeeds, then the matrix is positive definite. Okay, so obviously I haven't taught you about what that is yet, but it's something that that we're going to learn about next lecture, and it's actually the practical way that you'd actually test whether a given matrix is positive definite or not. If you were to ask the question of a matrix, is it positive definite, then this is what, for example, MATLAB would do to find out for you. It would attempt to compute this factorization that we don't know about yet, and if it can, then that means that the matrix is positive definite. Okay, so one last thing. Let's just, number 3 there, I'll just show you that that one there is the test you use for the second derivative test in calculus. Okay, 3 is like, sorry, second derivative test in calculus comes from 3. Okay, so let's just say I've got a function of 2 variables, f of x, y, and we find stationary point where the gradient of f equals 0. And then, if you remember from first year, what you probably did was something like this. If fx x star y star is greater than 0, and fxx fyy minus fxy squared greater than 0, then it's a minimum. Okay, so you remember seeing something like that? Well, that's basically testing the two submatrices testing the determinants of the two submatrices of the Hessian. So the Hessian and for a 2 by 2 case just looks like this: fxx, fxy, fyx, and those two terms will be equal, and fyy. First expression is just that first entry. Okay, so that's A1. In fact, if I make that not, yeah. Second test is that det A2 equals 0. So we've just done this principal submatrices test on our Hessian, and if it's positive definite, we get a minimum. And the other cases from your second derivative test apply here as well. Okay, so that's where I'm going to leave it today. Next time in class we're going to prove these various tests and maybe do a little bit more depending on how much time we have. And our next actual lecture, we'll look at the Cholesky factorization that I've started talking about. Okay, until I see you next time, have a good week.